Hello everyone, I'd like to welcome you to my talk. First, I would like to thank the organizer for giving us the opportunity to share with you today our latest development at Charles River. It's a cube assay that is targeting a voltage-gated sodium channel, NaV 1.9. So NaV 1.9 is an interesting target because it's correlation to pain. And we've heard already today about pain, but allow me to recapitulate and echo the importance of finding alternative analgesic strategies, because the current strategies now relies on opioids, and these have shown to have side effects like addictive potential, sedation, and confusion. So we really need to find an alternative for opioids. Now, pain is a sensory experience. You get your noxious stimuli. These noxious stimuli can cause danger. They're either an actual danger or potential danger. They are picked up by the dorsal root ganglion, which are known as nociceptors, transmitted to the central nervous system to be perceived as painful. When you have a pathology in this pathway, like inflammation or nerval injury, then you would start suffering from chronic pain disorders, which we have heard about today, and how important it is to have analgesics for chronic pain. As an alternative strategy to opioid, the sodium channel blocker, finding a sodium channel blocker, have aroused to be very interesting. In the nociceptors, we have three main sodium channels, NaV 1.7, NaV 1.8, and 1.9. And today, I'm focusing specifically on 1.9. 1.9 is a very peculiar channel. It has a different biophysical features from all the other NaVs. And it has the slowest inactivation kinetic. It has shifts in activation and inactivation voltage dependence, in the sense that activation voltage dependence is more in the hyperpolarized range. Inactivation is more depolarized. What does this mean? That would mean that it starts opening at more negative potentials close to the resting membrane potential. So it would impact the resting membrane potential and therefore impact the neuronal excitability. And that's why this channel is known as the threshold channel. If it's a threshold channel, it is no surprise then that the gain-of-function mutations that were identified in human patients, when we study them in heterologous systems, for example, they would show neuronal excitability of the cells, of the neurons. And to give you a brief overview of the mutations and how they are linked to mutations of NaV 1.9 and how they are linked to pain disorders, this is a schematic diagram of the alpha subunit of NaV 1.9, and in color you have the different mutants that were identified, and they have been linked to several pain disorders, ranging from increasing pain sensitivity, like familial episodic pains, or even loss of pain in congenital insensitivity to pain. So it's very, very important to look at NaV 1.9 when we're looking for strategies for analgesics. And just as a side note, since we're looking at the schematic diagram of the alpha subunit, NaV 1.9 is formed of alpha subunit and beta subunits. The alpha subunit would be the main conducting subunit, so it's a classic voltage-dependent channel. We have 6 transmembrane segments that are repeated 4 times. S1 to S4 is the sensor, S5 and S6 are the pore. That would be your alpha subunit. But you also have beta subunits, and these are important for trafficking the channel to the membrane, and they can also play a role in the regulation of the channel. So I would love if you can keep that in mind. Now, coming back to the importance of NaV 1.9 in pain. If I'm saying that NaV 1.9 is that important in pain, then I would expect that at least we have sought out to look for drugs that target NaV 1.9. But the actual situation is we do not have a selective inhibitor to NaV 1.9. There is a significant delay in the drug discovery process when it comes to NaV 1.9, even though 1.7 and 1.8 have been extensively studied. And the reason for that is that we do not have a stable cell line for NaV 1.9. The studies where we looked at the biophysics of the channel have relied mainly on isolating the DRG neurons and trying to block other sodium channels or having a knockout of NaV 1.8, for example. These are very insightful and very helpful because you can learn about the biophysics. But when you come to think in an industrial place where you want to run a high-throughput system, this laborious procedure is really not that effective. So you really need a heterologous system a stable cell line that you can put on an automated or high-throughput screening system. Okay. So because of that need, there have been already few successful stories in the market. They have been relatively recently, starting in 2016, where people have reported, despite the challenge and how difficult it is, some strategies that could help have some Nav 1.9 current. And most of these cell lines, you would appreciate that current amplitude is small. We were very happy to see actually Nav 1.9 currents when we can. And these strategies include pre-incubation of the cells at 28 or 30 degrees, for example, or co-expressing the beta 1 and beta 2 subunits. So these are the auxiliary subunits I mentioned with a 1-to-1 ratio. As we were motivated by the need for having a cell line to use for the drug discovery process, and we were guided by the information in the literature, our team at Charles River decided, okay, we're going to aim for generating a stable cell line for Nav 1.9, and we're going to use that cell line to design a cube assay that is useful for a high-throughput screening system. And today I would like to share with you our journey. First was the generation of Nav 1.9 cell line. So that's a brief overview of how we did it, and this is our experienced cell line generation team. So they followed 3 steps. The first one was to express the beta 1 and beta 2 subunits, and they designed the constructs with the aim that we have the 1-to-1 ratio that was reported to be helpful. Once we got that done, then they transfused the cells with the alpha subunit. And eventually, once we had our clones, then we can test those on the cube, and we can have a look at the biophysics and the pharmacology of these cells to validate that the clones that we selected are expressing Nav 1.9 currents. So when we look at the biophysics, the protocol that we designed, we went for voltage steps from -120 to +40, and then we had a constant step at -30 millivolt. And this is the current traces that we got. And just by looking at those traces, before analyzing, we could see the characteristic slow inactivation. And just to imagine how slow it is, this is Nav 1.9 in comparison to 1.8 and 1.7. It is significantly slower. You cannot confuse them. So we were very happy to see the current recording in the very first experiments. And then we started analyzing our data. We plotted the normalized current versus the voltage to get our IV plot. And we could see that the channel would start opening around -60, and that the peak is around -30, -40 millivolt, which was expected and seen in the literature. So the values that we're getting are consistent with what we expect. And then we looked at the inactivation voltage dependence, and for that we plotted the normalized current in response to this constant pulse versus the pre-pulse potential to get the inactivation V-half, which was around -40. And here I'm talking about the fast inactivation, which is occurring in the milliseconds range, since I'm having a pulse here of 100 milliseconds. So it's enough to induce fast inactivation if you have a 100 millisecond pulse. But there's another sort of mechanism of inactivation, which is way slower. It requires seconds to develop. To have a protocol for that, we had a constant pulse, which is going to -30, and we repeat that 10 times with a 20-second interval, so that you get a block of, let's say, 200 milliseconds, where the cells are exposed to the same holding potential. If you vary the holding potential, then you can use this holding potential to induce inactivation. So you can have a holding potential from -140, -120, and so on, -60. And in response, you can see the current decreasing as the potential changes. And then we looked at the normalized current versus voltage, and we got the V-half of slow inactivation, which was around -90 millivolt. Both values agrees with what's already in the literature, further confirming that we have an Nav 1.9 current. And looking at the pharmacology, Nav 1.9 is famous for being TTX resistant, so that's the first compound we look at. Up to 1 micromolar, we do not get a response, which we were very happy to see. And then we looked at other 1.7 and 1.8 blockers that were in the literature. Some of them were already published in the literature, so we can confirm that the IC50 that we got was within threefold of what was in the literature, which we were very happy to see for the majority of the compounds. We also were very happy to see how the quality of the CRCs, the concentration response curves that we're getting, because that gives us confidence in the assay quality that we're using, and that is suitable to use it for routine profiling when we want to test our compounds later on. So now that we have the cell line, we validated that from the biophysical property and the pharmacology, you indeed have an F1.9 stable cell line. We wanted to design the QSA, and for that, we started thinking about the voltage protocol. Well, there was different versions of it, but eventually we had the simplest one, a minus 30 millivolt pulse. And the holding potential we're using is minus 140. Minus 140, to remind us, it's at the top of the slow inactivation curve, so you don't get any inactivation, you get the maximum current that you can get. And when using this pulse, you can simply repeat it under different conditions. You start with the external solution, you add your compounds, and then you add tetracaine, in our case, to use like full block, completely blocking your compounds. And just to give you a brief idea how our plates are designed. So again, these are automated patch clamps. You're doing 384 wells recording. You're plating your compounds in 384 wells. The first two columns are we dedicate for our controls, and the rest are usually our compounds in single concentration. To mimic a single concentration layout, I'm here using a reference compounds, CRCs, randomized so that I can see if I'm able to pick it up using my assay. And that would be the readout that I get using the Sophine Analyzer software. So once you have it set up, it can show you the % inhibition in each well. I would first look at my controls, well, around 100%. Around what I put the tetracaine, I found the 100%, and here I found around 0, so it's behaving as I expected. And then I'm getting around 90% where I have the highest concentration of tetracaine, so it's following what I expect. To analyze these data and judge its quality, I'm looking at 2 points, success rate and robust subprime. The success rate represents how many wells have passed QC. For QCing efficiently, in Analyzer, you have the option to set automatic filters. You can decide what's acceptable for resistance and capacitance and current, and it can automatically fail wells. And then you can look at your hits, which are the most interesting wells for you, and can judge the quality of the recording. After we fail those wells, then we start calculating how many wells have passed. I need, in a single channel, in a single concentration plate, I would recommend to have 80% success rate, so that at least I have 80% of the data that I can trust. For the robust subprime, that's a measurement for how well the controls are separated, and usually you want that above 0.4. So what we did is we had a pilot study. We had 7 plates. We ran those as a stacker to see if the cells can tolerate having a 7-plate stacker. And the success rate and the subprime were monitored. So there were 7 plates and 2 repeats, and in both parameters, we get them well above the thresholds that we wanted. This means that our assay is performing nicely around 6 hours for those 7 plates. And in this pilot study, we managed to actually screen 6,000 compounds already, although that was just a validation study, which was really nice to be able to do. We then looked how well the data actually correlates for both replicates. So we plot the percentage of inhibition for replicate 1 and 2. And this is the control. So in green, we have the DMSO around 0. In red, we have the tetracaine around 100%, and in standard is in between. And then the compounds are lying in between. All of those data points correlate nicely, so we have 95% of data correlating quite nicely. We were then interested, did we see any hits? I mean, it was just a validation to see that the assay is performing nicely, which it did, but it would be nice also if we can identify hits. And we were very happy to see that we actually got around 1% of hits. Here, on the right, I'm showing in blue an arbitrary cutoff of 30% for each replicate. And in red are the data points that are showing more than 30% inhibition in N1 and N2. So that was a very nice outcome of this pilot study. So in short, we validated the assay for a single point screening. And this was using the resting protocol, but we all know that the inactivated protocol is quite interesting for physiological reasons, so we tried to think of a different protocol. And for that, we had a secondary assay where the holding potential was minus 90 millivolt. The reasoning is it's close to the V-half. It's the V-half of the slow inactivation. So we're trying to have around 50% of the channels in the inactive state. And we follow the same thing, external solution compound full block. And just to validate that the assay is doing what it's supposed to do, this is the current amplitude in the external solution. In resting, you get an average 2 nanoamps. In the slow inactivation, average 0.7. It's close to 50% of the current that you have, which means that I am inducing the inactivation I need. And using the secondary assay, we use this for routine profiling. So we tested the compounds that we did for the pharmacology using the resting protocol, and we looked at the IC50. And we wanted to see, do we see state dependency, if there is a difference? In the majority of them, we don't. We mainly see for tetracaine, and these values have been reported already in the literature, and they agree quite nicely with what we got, which is a further point that validates and makes us trust our assay that we have. So for the state-dependent assay, we intend to use it mainly for routine profiling, but it's also useful as a secondary assay for doing the screening process. And that's because the current amplitude is way smaller, so the variability is higher. So if you're just doing a single point screening, yeah, it's less sensitive than the resting protocol. So it's useful as a secondary assay. But we strongly trust it when it comes to routine profiling because we can generate concentration response curves that we do trust. So in conclusion, CRL has successfully generated an Nav1.9 cell line, looking at the biophysics and looking at the pharmacology profile and the characteristic slow kinetics. We were able to have a cube assay that is suitable to run for high throughput screening, whether that is for routine profiling, so CRC curves, or whether we're doing single point concentration. It was also even used already for a client where we screened 300,000 compounds. And it successfully ran smoothly, and we were very happy to see that. Because we know that we're interested in state dependency, we developed an additional assay that can be used in parallel, and we used it already for 9,000 compounds, where we can have it to guide our decisions when we need to. So in short, we have the cell line. We can run it as a high-throughput screening system. This is a very important step that would facilitate the drug discovery process for pain relief treatment, and hopefully, at some point, we'll see more alternative strategies to the opioid treatments that we have. And last, I would like to acknowledge our teams that have worked really hard for this project. Our cell line generation team, Kelly, Thompson, and Arnold. Our ion channel team, Hannah, Russell, and Stefano. And I'd like to let you know that we also have a poster if you have any questions. We're very happy to answer your questions. And Russell is with us today. You can approach me, Russell, if you have any questions. We'd love to answer them.
Thank you very much for this nice talk. During my PhD, I had the pleasure to make a stable cell line. And in the course, I picked several clones, I expanded them and characterized them. Also, when it comes to growing conditions, for instance, or how fast they grow in a cell culture and biophysics. And I saw a subtle difference between each of the clones. So some were growing faster, the others slower in cell culture, slight changes in the biophysical properties. So did you check for several clones?
So we had several. We tested 15 clones. I don't remember on top of my head how many were showing Nav1.9 currents. We had actually 2 strategies. So in total, we tested 30 clones. And we had a quite good success for one of the strategies that the majority of those 15 clones actually showed a Nav1.9 current. In terms of biophysics, it was consistent, so we were very happy to see that. So there was no reason to pick one clone over the other in terms of this one is showing better biophysical property or not. We did see a difference in the growth rate we have no explanation why this one clone is growing differently from the other. So there were a few differences that we cannot explain. But yeah, they were not identical in that sense. But from the biophysical point of view, we haven't observed any differences that was driving us to choose one clone over the other.
Okay, thanks.
Okay, question over here.
Hello, very nice talk. So all the known molecules you tested, they probably all act on the pore. Is there any gating modifying on non-pore acting molecules known for 1.5, 1.9?
Gating modifiers?
Or any modulator that work along, apart from the pore side?
Going from the pore side.
Yeah, you had succession chain.
Yeah.
Oh, I see.
But active for 1.9, it was not active.
I think that Genentech compound is in the pore compound.
Okay. Okay, thank you.
Yeah. Yeah.
Okay, further questions? So how long did the screen take? Was it 9,000 compounds?
So the initial phase were 300,000 compounds, and then we had a phase of 9,000 compounds.
And how long for the 2 periods? 2 screens?
So there's a waiting period in between, couple of months.
Okay,
So yeah.
that's brilliant. Well, very well done.
Yeah.
So I'd like to thank all the speakers this morning. Thanks, Catherine.